Hello students, welcome to Inside Physics. Today we are going to discuss about interference in thin films. So this topic is a unit of wave optics which we are going to discuss today. So before going to the interference pattern in thin films, we should know what is a thin film. So it is an optical medium where the thickness is very small. So it is almost equivalent to one wavelength of light, that is lambda. So any optical medium of thickness equivalent to one wavelength of light is considered as a thin film, and we can also say the thickness will be in between zero point 0.5 micrometers to 10 micrometers. Okay, so this thickness is very small, and most of the thin films are transparent sheet like structures made of glass or mica, or an air film is also sometimes considered as a thin film if it is of thickness in the order of this zero point 0.5 micrometers to 10 micrometers. Before understanding the interference pattern in thin films, we need to know some definitions of optical wavelength and geometrical path length. Optical path length is called OPL, and geometrical path length GPL. So if we can understand what these two are, then we can have the derivations in this topic. So OPL is nothing but optical path length, and GPL is geometrical path length of the light. When a light is traveling in a particular medium, suppose if it is air or vacuum, then we know, suppose a point A and a point B, a light travels between A and B. If you can have the shortest distance between A and B, it is considered as geometrical path length. And when air and from the light is entering from one medium to other medium, and suppose it is entering from medium 1 to medium 2, and the second medium having a refractive index of mu, then that means the light will travel mu times lesser, with velocity mu times lesser in the second medium, so that the distance covered in the second medium is also takes mu times more time than it is compared to the first medium. So that is the difference between optical path length and geometrical path length. These two are matched with an equation like this: OPL is equal to mu into geometrical path length. That means the optical path length is considered as the path followed by the light in the second medium. So it will be mu times the geometrical path length of the first medium. So when it is entering from one medium to the second medium, and if it is considered as air to glass or air to water, so the second medium will have a refractive index of mu. So with this relation, we'll be having the optical path length, and thereby we can have the optical path difference of a light ray when it is passing through the second medium, and it gets some part of refraction and reflection at the boundary of two mediums. Optical path difference. So this is the criteria to understand what is the phase difference. By understanding the optical path difference, we can understand the phase difference. So by understanding the phase difference, we can derive the conditions for maxima and minima. So whether the rays are interfering to form a constructive pattern, or they are interfering to form a destructive pattern. So these patterns are called constructive interference and destructive interference. So what is optical path difference? So when the ray is entering a medium and it is again leaving the medium, so the path difference between the two rays is called optical path difference. So that is generally represented by delta, and if the optical path difference is suppose lambda, we consider the phase difference, equivalent phase difference will be 2 pi, for lambda is one wavelength of light. So in this way we can get the phase difference by understanding path difference between the two rays, and the two rays are coming from a single ray, but they are being refracted in the second medium, so they will travel in two different paths, and the two rays will be having the optical path difference because they are traveling from one medium to another medium. So here, by understanding these terms, we can have a look at this diagram to go through the interference pattern. See, this is the incident ray, this is the thin film we are considering. The thickness of the thin film is T, and the incident ray is incident at this point. This is called point of incidence. So this is the B point and this point is F. So what happens here in thin films while an incident ray is incident here? Some part of ray is being refracted, that means it passes through the second medium, and some part will be reflected back. So again, because it is traveling from rarer to denser medium, so the refraction will be towards the normal. This is the normal of the interface, and again here at the point of incidence, because it is moving from denser to rarer, the refraction will be away from the normal. Here again at the point of incidence, some part of the ray will be refracted and some part will be reflected. So this refraction reflection percentage, I have given you the details in my previous video, which is thin films. So you can have a look at that. For now, we will consider here the loss of reflection and loss of refraction to understand this diagram, so that we can calculate the optical path difference. By that we can have a derivations for maxima and minima. That means constructive interference and destructive interference. So if you see, while incidenting at this interface, that means border of the first and second medium, you observe this thin film. The thin film is bounded by two borders which is having air at the both sides of this thin film. So here from B, the reflected ray goes along this direction, that is BC is reflected ray, and again the reflection is happening at D. This at the point of D, the refracted ray is also passing through the air medium. So this is happening at B is refraction and reflection, and at F there is a refraction and reflection, and this reflected ray is again being refracted. If you look at this is denser to rarer, so that is it is refracted away from the normal. We can draw a normal here also, just like this, to understand that it is going away from the normal. So in this way we observe the points BF and FD. So what is the optical path length here is equal to mu into GPL. We know that geometrical path length. What is geometrical path length? Path difference we need to take. So BF plus FD minus BH. If you observe the geometric path difference, you can say while the ray is passing from here to here and here to here, and again it is refracting from this medium, in this time while the ray is refracting here and again it is being reflected, in this time the reflected ray at this point will be traversing from this point to this point. So here the geometrical path difference we can say is nothing but see, BF plus FD minus BH. This we can say is the geometrical path difference. So that means we can easily get the optical path difference by writing delta difference is equal to mu. This can be mu into BF plus FD because this path is in the medium where the refractive index of the medium is mu. Okay, this is mu refractive index and this is the T thickness of the thin film. So by this we can get the optical path difference with these calculations, and how we need to calculate we will see here. So if this is the incident ray with the loss of reflection, we can also say this is the reflected ray, and angle of incidence and this angle are same as per the laws of reflection. And here also the angle of refraction, if this is the angle of refraction or this is also angle of refraction, and thereby with the loss of reflection this r and this r are both are same. If this is the angle of incidence, by symmetry with the properties of triangles we can say this angle is also angle of incidence, because see, for this line this is the perpendicular and for this line this is the perpendicular. So if these two are the having an angle of incidence here, and this is also having the same angle of incidence, so this angle is 90 degrees because this is the perpendicular drawn from this H to D, and this is the perpendicular of the BC ray and drawn from the BC ray to the point D, and this is 90 degrees. This is I, this angle can be 90 minus I. We will see the angles here. HBD, angle HBD is equal to 90 minus I. Angle HDB, angle HDB is equal to I. And here this angle BHD, angle BHD is equal to 90 degrees. So these are the angles from this triangle HBD. So if you observe BF plus FD, so if you take here tan R, what is tan R? Opposite side by adjacent side, right? So here we will take tan R here, and the opposite side is BG, that means tan R is equal to BG by FG, right? That implies BG is equal to FG tan R. So what is Fg? Here from here to here, that is the thickness of the film, that is T tan R. Bg is equal to T tan R. So we know that Bg plus Gd is equal to Bd, right? So this is also equal to Gd. We can also equate this as Gd. So Bd can be written as 2Bg, that means 2 Bg is tan R, that means 2T tan R. So the length BD is taken as 2T tan R. So here the path difference we have taken as optical path difference as BF plus FD minus PH. Okay, now we need to calculate what is BH here. Okay, see, BD has come as 2T tan R. Here now we calculate BF and FD. So we can say that cos r is equal to this adjacent side by hypotenuse. What is adjacent side? FG by BF. That means T by BF. So here we can write BF is equal to T by cos R. So this BF is equal to FD, so that you can also write FD is equal to T by cos R. Both are same. So by this I can write, say, BF plus FD is equal to 2T by cos R. So I am adding this term and this term. I got 2T by cos R. Now I got this BF plus FD as 2T by cos R. If I can get the BH value, so I will get the optical path difference, and so that we can proceed to calculate the maxima and minima. So how to get the BH? If you observe this triangle BHBD, so here sin I is equal to opposite side by hypotenuse. We know that sin I is equal to opposite side by hypotenuse. So there, from triangle BHD I can write sin I is equal to BH by BD. BH by BD. BD value we already got here, 2T tan R. Okay, so from this I can write BD is equal to, or BH is equal to BD sin I. So BD is nothing but, that implies this is equal to 2T tan R sin I. Okay, so this BF plus FD we got, and BH, here the BH value we got, but here if you observe sin I, we know that from Snell's law mu is equal to sin I by sin R. So that implies sin I is equal to mu sin R. So we know that we can have this equation from the Snell's law. So if you replace sin I by mu sin R, so this becomes 2T tan R. Sin I is replaced by mu sin R. Mu sin R. Okay, so I am erasing these terms because the space is not enough. So I got BH as, like, see, I am writing here again. From this step I am writing here BH is equal to 2T tan R. This tan R can be written as sin R by cos R. Sin R by cos R, and again mu sin R. Okay, so what happens to this term? This becomes 2 mu T sin square R by cos R. So finally we got BH is equal to 2 mu T sin square R by cos R. BF is equal to 2T by cos R. So we have written at the beginning the optical path difference is equal to mu into BF plus FD minus BH. This is what we have written. So these two terms we will substitute here in this equation. So we will get mu into Bf plus Fd is nothing but 2t cos r minus what is Bh? We got 2 mu t 2 mu t sin square r by cos r. So finally we have got the optical path difference as in this form. So if you simplify this one, this equation, you simplify that one, we finally get the optical path difference as 2 mu t cos r. Okay. Delta is the optical path difference. We have given the symbol for that. And here we got 2 mu t. By simplifying this one, this term, we will get this, because we need to get the simplification. After that we will get this equation as 2 mu t cos r. Here there is a small correction because of the path length that will be changing at here the point of reflection. So if any medium from rarer to denser, any light from rarer to denser is incidenting at a point, and at the point of reflection it undergoes a path difference of half wavelength, or if it is taken as in the phase calculation, it is a pi, change of pi phase difference. So a path difference of lambda by 2 from here to here will occur at the reflection happening at the two mediums at the border, and this is the point of incidence. So if you correct this equation, and the exact path difference, optical path difference will be minus lambda by 2. So this is the exact optical path difference when a light ray is passing through a thin film, and it is the thin film is bounded by two boundaries, and in between it is having a thickness of t. Okay. So with this optical path difference condition, we can arrive at maxima and minima. So first we will see how the maxima will happen. That means maxima means it is a constructive interference. Here see, the two light rays reflected from here and the light ray being refracted here will be in the same phase. If you take the light ray incident passing from this point to in this way, and it is coming from D2 to the passing through this way, and these two light rays will be forming the interference pattern, because the conditions of interference are satisfied here. It is the conditions of interference, see, they are of same coherent light source, so the monochromatic single source of light, and they are also having the same phase between them, and they are of same frequency, because they are divided into two rays because of the single incident ray. So the source is a single source, so that it is divided because of reflection from the thin film, it is only divided into two rays. So that is the difference here, because the interference pattern in thin films is because of the reflection, not they are directly interfering, they are not two coherent sources here, only the reflected ray from here and the refracted ray from here are behaving like as two rays that are being interfered, so that they are of same coherent source and they are of same phase or constant phase difference. So the interferent conditions are obeyed, so these two rays will form the interference pattern. So if you observe the interference pattern based on the optical path difference, here the condition for maxima will be the optical path difference is an integral multiple of one wavelength. 2 mu t cos r minus lambda by 2 must be equal to m lambda. Then the condition of maxima will be satisfied. So the two rays, ray 1 and ray 2, will interfere constructively to form the bright fringe. So that means they will have a crust to crust correspondence and trough to trough correspondence in the wave. So if you have observed this equation, this will become 2 mu t cos r is equal to m lambda plus lambda by 2. So from this we can write 2m plus 1 into lambda by 2. Okay, so here I have taken this as LCM, and this lambda by 2 is being taken out. So this is the condition for the maxima, and we see what is the condition for a minima. So if the minima, that means the destructive interference where the intensity of light is 0, is to be happened. So the optical path difference minus lambda by 2 is equal to, it should be the odd integral multiples of half wavelength. It should be equal to half integral multiples, odd integral multiples of half wavelength. Then the conditions of minima is satisfied. Now by simplifying this equation, we can easily write it as 2m plus 1 lambda by 2 plus lambda by 2, right? So here this will become, if lambda by 2 is taken out, so this will become lambda by 2 into 2m plus 1, that means plus 2. So further we can write it as, so m plus 1 into lambda. So if you observe the condition of minima, so this minima condition is occurs when the two waves are forming a destructive interference pattern. That means they will have a crust to trough correspondence. So the amplitude of the wave is being becomes 0 because of the destructive interfering. This is equal to cos r equal to this one. So we have the condition satisfied for maxima in this form, and this is satisfies the condition for minima. So in this way we can understand the interfering pattern in thin films. See here, the reflection is the cause for interfering in thin films, and in this process, with the process of reflecting interfering waves, the Newton's rings pattern is also observed, where the air is considered as a thin film, and we can form the Newton's rings, and thereby can be observed through an optical instrument like a traveling microscope. So this is what all about the interference in thin films. So in the next session we will see some more topics in wave optics.